Okay, so we will continue and finish this session about these two concepts actually. One is about embedding into probabilistic trees in general and in particular for cut problems. And the second one, oblivious routing. As I mentioned, that was somehow the set of results that result in this probabilistic embedding into trees. We will finish them. What would be the rest? So these are like kind of three things that are essentially we discussed. Then we will go to a special graphs, especially planar graph. We talk about bidimensionality theory. Again, it's a big theory that can solve lots of problems for planar graph and much more general than planar graph, H-minor free graphs in general, lots of sparse graphs. We talk about big graphs and in particular some the first streaming algorithm that you could do some kind of sublinear on this big graphs next. And then we will go to some particular problem which are important, very important in network design, like facility location, primal dual algorithms for like Steiner tree or price collecting problems. Talk about k-median iterative rounding. Iterative rounding is a general technique to solve a problem, or like group Steiner tree. These are the very basic problems that exist. And these are like the techniques are beautiful and can be used for lots of other problems as well. So that would be for the rest of the class. But let's finish this concept first about the oblivious routing. Again, this was the oblivious routing that you wanted to have a graph for each pair SI TI, and you had the demand. You want to find some kind of fixed routes that independent of what are the demands that are coming and what are DIs. Then you want to have, if you are using your routing path, it is much better than it's comparable to the optimum within a factor polylog in general and log more importantly. Good. So then we discuss about this trees, this concept of load and R load. That was important. Um, so that we said that you have we discussed that you have this graph G, and then this is the tree T that you have it, and we discussed that these are the set of no, the leaves would be corresponding to vertices here, and also each vertex here it goes here. So this is 3T, and we had this kind of Steiner points, or we could show that actually, and then we have only one tree. This is the first Racket 2002 result, and then you might have actually no Steiner points as well, or you can have several. But in this case, also we have several trees. Here you can have a Steiner tree or no Steiner tree. That would be much easier if there is no Steiner point. So this set of vertices would be exactly the set of vertices of G. But in both cases, we needed to define these two concepts. This is corresponding to distortion that we defined for. This is corresponding to the concept of distortion that we defined for Bartal or FRT embedding. So to do that, we need to define the load of an edge. So the load of an edge, as I mentioned, you will go through all edges of the graph, all edges in the tree, like ET here. And you want to see what is the load on one particular edge. You will go over all ET, that the path ME of ET would be the path so the path corresponding to, as I mentioned, so this is UV. So here, this is UV, here there is U, this is V. If this UV, it goes through this edge E here, edge E here, then you need to sum it up the C of ET. And what was the capacity of each edge in the tree? Each edge in the tree, we knew that if you remove it, then it would be a partition of essentially you have a, mm, you have the partition of vertices here. So you have a partition of vertices here, this partition in the graph. That would be the capacity of this edge. And the set of edges that are going from this to this in the graph, all such edges would be the capacity of this edge. So this capacity is fixed. So capacity, we know that. Now, for each, now what is the load of an edge E? The load of an edge E is that for each edge that you are considering here in the graph, you see what are the three edges that their path goes through E, and then those edges, C of ET should be added. So that's the load of this. This is independent of somehow multi-commodity flow at this point. And the R load or relative load would be the load of this over C. So the results that essentially all the results that we are talking about are this one. It means that like either there is one tree that we will discuss, or there is a embedding into probabilistic trees, such that this maximum, what is this maximum? So we say that essentially max of E belong E in the edge set, or R load of Ti times the probability distribution of this 3Ti over Ce is at most B. Or you can say that essentially you want to make sure that for all E, so this is sigma of I of lambda I load Ti of E is less than B times C of E. And here, as I mentioned, we had, so this load Ti is somehow, this Ce it would be essentially corresponding to distance. And we discuss essentially distance is equal to 1 over capacity. So here, this C is the capacity. We had the distance in Bartal or FRT. And here we had the distance, but we have the load of this edge essentially. And we discussed this one. This is an interesting formula. Let me go this one. Let me, yes, so let me define this load and then I will come back here. Yes. So let me just, so this load that I have mentioned, you can actually have a simpler formula for that. So you can write essentially the load. So the load T of E, this is the formula that we mentioned. For each edge in the tree that E belongs to that, you will consider that if E belongs to the path corresponding the path to this E of T, then you will just sum it up the capacity of that edge. Then you can actually, then what was the definition of capacity of an edge? This is the one that I have mentioned. Essentially, for any edge E prime that belongs to the cut corresponding to ET. When you cut this ET from the graph, it partitions the set of edges into two parts. And this two parts in the graph, you see any edge there, you need to consider the CE prime of those edges in the graph. Now, you can actually change these things and change the order of this summation or the indices there. And you say that for each E prime belongs to EG, if ET is the unique path corresponding to E prime and E belongs to this path, then just sum it up C of E prime. this turns essentially into this equation. This is actually interesting thing. Is says that, so what would be the load E of one edge essentially in the graph would be T of E prime E times C of E prime. So to find a load of an edge, you just so load an edge in the graph G. You will consider what are other, so this is E, consider all other E prime that their path, their corresponding path in the tree actually goes through E. So just essentially, so here T E prime of E is the number of times E appears in M prime E of E prime. So essentially, these are the number of times that this edge E appears on this edge E prime. This edge E prime, as I mentioned, so in general, if you have a tree, this E prime, it may appear actually several times because this is an edge between two vertices. So the number of times that E appears on this path would be T of E prime E. That times the C of E prime would be essentially equal to load T of E. So this is a general formula that works for any tree with possible Steiner points, as we mentioned. And again, here for Raki is especially important because we can have one tree. In Bartal, we couldn't have one tree, essentially. And here, Steiner points really do some job because, like, first, without a Steiner tree, Steiner points, we cannot have one tree. But with Steiner points, we can have one tree. But in FRT, even with Steiner points, we cannot have one tree. So we can have probabilistic embedding into trees. So, this is important. Now let's consider the case that here, instead of one tree, we have several trees. And each of them, I mean, the simplest case, the most interesting case, or easier to understand, that each of them is the subtrees of the original graph. So, if it is the case, each of them is a subtrees of the edges. So, so if each of them is a subtree of this edge, then actually you can see in this case, as I mentioned also previous time, then what would be the load T of E? The load T of E essentially would be just, I mean, consider any edge here. So if you consider one of these trees, this T, and then if you consider one edge here. So like here, in this tree, so this is E. No, I want to see this one essentially. T of no, what is this summation? This summation says that those edges that their path on this tree goes through E. So who are those edges? Those edges are exactly this. Let me just draw. So this is actually the tree. So this tree T is exactly, this is essentially those edges. If you say partition this guy to here. So this edge E actually partitions in this tree T to two set of vertices. And they say this is a spanning tree. So it partitions the set of vertices in two things. So who are these C, essentially, who are these E prime? These E primes are exactly those guys, that edges that are going from here to here. So these are the edges that are going from here to here. And then this is E prime in some sense. So what does this formula say? Say that sum over all these edges that are essentially their path goes through this edge, essentially means that the cut corresponding to this edge sum it up over all this capacity. And what is the TE prime of E? TE prime of E would be 1 because each of these edges, that's the only edge and only one time it goes through E. So in that case, essentially this will be removed and that would be essentially, T of E prime E is the number of times essentially. So here you will sum essentially over all edges in graph that their path goes through E. It means that essentially all edges that when you remove this E, you have this partition of vertices into two sets, the edges that are going from one partition to another. That indeed means the capacity of CE. This is exactly the So this is exactly this the whole formula would be C of E in the tree. So this TE prime of E is a more general. Then we have a Steiner, essential Steiner points, and each of these Steiner points is corresponding to some vertices in the graph. Yeah, that's the thing that we mentioned is the original one tree of Rake. But if you have just a tree which is a spanning tree, and in this case we have probabilistic embedding, then load T of E would be just the capacity of that edge. If that edge essentially is present in the graph. If that edge does not present in the graph, all this T actually would be 0. So in that case, would be the whole load would be 0. So if the edge belongs to the tree, it would be this CE of T. So if E belongs to T, and it would be 0 otherwise. Now, let's go to this R load things that we discussed. So here, we had, as we mentioned, so we mentioned that sigma of so what do we have here? We have sigma of I, lambda I. So lambda I is the probability that we are embedding into this 3ti. Load E is less than or equal to beta, so B times, you can call it beta times C. And as I mentioned, so this, and we know that this B essentially you can get log n or O theta log n, depending whether you want to have a spanning trees or just some trees. And then what was the load E? Load E was the one that we mentioned. This is the definition of a load. This is a load Ti of E. So you can say this is the Ci of E. And if E belongs to Ti, if E belongs to, and 0 otherwise. So 0 would be otherwise. Good. So this is the things, and this is the one that if you consider spanning subtrees essentially. Spanning trees. Now let's see, and we know that this is this beta atmos order log n. I will talk about this. By the way, yeah. Let me give an example. How can we use this one now to solve a cut problem on trees? In particular, the bisection problem. So let's go to this one. So what is the bisection problem? So bisection problem, as I mentioned also previous time, is like this. You have a graph of n vertices, say n is equal, n is even. You want to divide it exactly n over 2 or n over 2 If there are n is odd, then you want to consider ceiling and floor there, such that then some of the, and each edge has some capacity or some weight, and you want to minimize the sum of the, so you want to minimize crossing, like the weight or capacities of crossing edges. So that's the thing that you try to minimize. And it is super important that each of these guys are balance cut, like these are n over 2 exactly. Because otherwise, it would be just min cut if you want to just divide it into two parts. It is important that this is some kind of balance min cut, that each of them should be n over 2. As I mentioned, this is important, this kind of bisection, because then if you want to do recursively, it is important that each of these sides goes essentially by a factor, constant factor down, in particular here 1/2, and the depth of any recursion. So if you want to solve essentially a problem on a graph, this is called divide and conquer. You can consider the whole graph, you will find the bisection, divide it into two, then solve these problems on each of them recursively, and then combine the solution to get the solution for the whole graph. And it is important to be n over 2, because then the depth of recursion would be like it. Otherwise, it can be n, which is very bad. And the depth of recursion is very important, because if you want to solve, for example, approximate solution, the depth of recursion actually comes as a one factor in your approximation solution. So this bisection problem is a very important problem. I mean, the people have considered a lot. There was a study paper, I think, by Uri Feige, that he obtains poly-like, and it is like very essentially very complicated. It's talking about a volume preserving embedding. You can read actually that paper, like Uri Feige and bisection, you will find it. But here, Raki essentially in the second paper, in Stock 2008 paper, he actually presented this one, that essentially this, here using essentially Bartal and some other problems, you can actually get this kind of trees for which we have this equation satisfied. This essentially expected load. So what does it say? It says expected load on this tree is at most beta times the essential expected capacity essentially on these trees is at most beta times the capacity of the edge E, with this definition of capacities. So we can do that. Now let's see how can we solve a problem like bisection on using this theorem. So let me go to, so this is a definition of problem that we just discussed. So in the minimum bisection, you are given a graph G with n equal to 2k. You want to partition the vertices in two parts with k vertices with minimum width. Width means total capacity of the edges, that essentially they are endpoints landing in two different things. So how we do, how should we solve the problem? So according to this tree embedding for the cut problem, you can find this tree T1 to Tk. So you will consider this T1 to Tk. Then you want to, and as I mentioned, say these are like spanning subtrees. So in that case, you consider this kind, like for example, this particular T among them. So you have, this is a subtree of the original graph. And again, it is important that capacities here are different. Capacities are corresponding to the cut there. Now, just solve the bisection on this one using dynamic programming. On trees, we can solve almost any problem using dynamic programming, in particular bisection. So what is the bisection on trees? You want to find essentially a set of, these are the set of nodes, n nodes that you have it, and you want to give each node, you want to color it with blue or red. such that some of the edges, the capacities of edges between blue and red is minimized. And you want to make sure that the number of blues and the number of reds are equal. How can you do that? This is a very simple thing that you can do it with dynamic programming. Essentially, you want to say for any node R, this is a dynamic programming that you can do it. But for any node, essentially, you want to say for X number of red and Y number of blue, what is the minimum cost? So that you can do it essentially. For the leaves, the basis of induction would be trivial, would be 0 for any X, Y. But when you come up, in this one, you can actually fill in the dynamic programming table just using that. So if you know this for your, if you want to compute this one for your the parents, just you can just use essentially X prime, Y prime that you have for the children, and for each of them you know the best solution. And depending whether this vertex itself would be red or blue, the root itself, so this root would be red or blue, you may sum some of these capacities as well, and so you can update it. And then finally, when you compute this one for the root of the tree, you just want to get that you have n over 2 red and n over 2 black and blue. So for this case, you see what is the entry of this one. This is the dynamic programming table of this. That actually is the one that gives you the solution for the this bisection problem. So bisection on trees can be done easily using this kind of bottom-up dynamic programming. And again, it's very simple. You can figure it out. This one I mentioned essentially the details. And this is the one that the dynamic programming table is the one that I have mentioned. For each node R, you need to say how many reds, how many, if it's X number of red, Y number of blue, what is the minimum cost that we can do it essentially. So that's a dynamic programming for on trees. You can solve the problem optimally. So what do? We are just considering this T1 to Tk. And now for each of them, because these are spanning subtrees, we just solve the problem. So solve bisection on each. Tree. So you solve here bisection on each tree. And then what do? Then you will just take the best solution. So then this one, and then take the best solution. And that's it. Now, okay, so I want to say that this one that we are taking the best solution, how do we find the solution on the graph? That is very easy. So let's say this is the 3T that we obtain the best solution here. Good. So here, actually, you can see that. So the solution that we obtained here, there are some of these are red, and some of them are blue. So this is red, this is blue. How many blue do you have? And say this is one more vertex. This is red. And this is red. So this you obtain the color. We are using the same coloring on G. So this is the same coloring of vertices that we are doing on G. Now, what can I say? I can say that. So here I want to say that the cost on G is at most the cost on T. Why? Because what was the thing? So here you are cutting some edges essentially. So these are the edges in between, correct? So this is, for example, oh, this was another one that I forgot to put it as well. So say this is red and this is blue. So here, these are the edges that you are essentially cutting. What are the edges? So these are the edges. For example, a red, blue, this is the one that you need to cut. This is the one that you need to cut. This is the edge that you need to cut. And this is the edge that you need to cut. I think these are ours. So these blue edges, essentially the edges that you will cut because these are the edges between blue and 6. But each of these edges is corresponding to the cut in the original graph. And the capacity of these guys is exactly the sum of the edges there. So if you just cut these blue edges, if you cut the cut corresponding to these blue edges in the original graph, its cost would be at most the CE of this edge. And if you cut all of them, then you will disconnect all blue edges, all blue vertices from the red edge, blue vertices from the red vertices. And the cost would be the cost of the edges in between. So this is essentially, this is the domination property that we had it before. Like when we consider at Bartal, that was like essentially a bit easier because this was a spanning tree and then the path exists in the graph. So always, of course, it was a solution. But here we are just cutting the edges. But these edges, as I mentioned, they have the cost of them in the graph and here are different. But if you just cut the corresponding cuts, the cut would be at the total cost would be at most the cost of edges in this tree. So that we know that. So we obtain a solution, its cost is at most. The only thing that remains to show is to show that so far we find the solution and we said, okay, in the graph you can get the same cost. The part that still remains is that we need to say what about opt? Why this is comparable to opt? And this is the non-trivial part that we need to essentially do it. So here we are writing exactly the same set of equations that we have written it before for Bartal. For example, I have mentioned for a Steiner tree or group Steiner tree, how we can solve on trees and then get the solution on the original graph. What was the equation that we had it essentially? So the equation that we have it is exactly this one. So the equation that we have is this. So we knew that log, so consider optimum solution. What is the optimum? So optimum solution essentially, it cuts, so consider the graph G. And optimum cuts some of this edge. Now, if this is opt, this opt, you can embed it on any of these trees. How? Because if you just cut, so some of these edges, maybe not all of them, if you cut any edge in this tree, if it exists, so you will cut in any of these edges in the graph, in each of these three, if it exists. If it does not exist, don't cut it because it does not exist. So it means that from opt here, so here from opt here, you get another opt here, opt of T essentially. So this is opt of G, this is opt of T. So this is opt of the original graph, this is opt of T. And so from this, any of these trees, essentially we get the same thing here. Why this is a solution for T? Because here the solution, it would be a solution for T because essentially any edges that exist in opt either does not exist in T, that you don't do anything, or if it exists, you will cut it. So any opt G you will consider, it has a corresponding opt T here, which is the solution for this. And of course, this opt T, the cost of that would be less than this, the cost of this guy would be greater than CT. What is the CT? CT is the optimum solution for this tree that we can find it safe using dynamic program. Because opt is just a solution versus CT, which is the optimum solution. And of course, we are taking the C star, which is the best among all trees. Okay, so let's see the equation. So what do we have here? This is first, we want to use this concept of load that we had. So this PT essentially is this lambda T here. So we had a probabilistic embedding into trees that sum of the load Ti of E times the probability of this tree is at most log n times C, the cost of this edge. So, by the way, one thing, when we cut this edge here, the cost of this edge here is different from the cost of this edge here. So in the optimum, in the graph, it is CE, but here it would be CE. Here, the one that we have it would be, yeah. So the one that we have here would be CE of, that would be CT of E. What is the CT of E here? So CT of E is actually here is, I mean, as I mentioned, the size of the cut corresponding to this HT. Good. So we have this essentially this equation that we have just mentioned, CT of E. Now, so this is the CT of E that we discussed. Now, what is the corresponding thing? We had that, so this, we had the load of this, essentially the expected load is less than or equal to log n times C of E. So log n times opt is greater than or equal to this. Why do we have this equality? This equality is exactly coming because of this because of this essentially expected load things that we have here. Why? Because consider each optimum, because essentially each edge that you will consider it, CE. So each edge here, CE, we know that the expected load of this edge would be, expected load would be at most log n times that. And what is the expected load? Expected load is exactly the one that the size of the cut that we are doing it. This is essentially each edge E, if you consider it. So we will cut it in different trees. The expected load of that would be essentially the expected cost of this edge that we will cut in all of these trees. So this essentially comes directly from this. So we have the log n times opt is greater than this. Now everything else is same as before. So opt T, we know that is, so then this PT is corresponding to this lambda T essentially. Now, what about opt versus CT? So here, opt of T is greater than or equal to CT because, as I mentioned, CT is the optimal solution for this one. And CT is, so this is essentially, instead of this CT, we can say that each CT is greater than or equal to C star because C star is the optimum solution over all trees. And then we can just factor this C star and some of the PTs would be equal to 1, would be C star. So we knew that essentially the solution that we will get on G would be at most this C star. And we know that C star is at most log n times opt. And this means that we have a log n approximation for the solution. This is the example that I have mentioned for bisection, which again, it was very important because the previous solution for that was a Fox-Stock paper, very complicated solutions. And here we have a much nicer and much cleaner solution with a much better approximation if you are doing this probabilistic embedding into trees, essentially. Good. So that's the part essentially that we have it. And so this was the thing that I wanted to cover. And again, this you can solve for any cut problems. Like there are different type of problems. For example, you may have a multi-way cut. Multi-way cut is essentially that you are given a set of terminals and you want to cut a set of edges such that each of these terminals essentially are disconnected. This is called multi-way cut. So multi-way cut is somehow is the dual of Steiner tree problem. You may have multi-commodity, which is somehow dual of Steiner forest. You are given a set of pairs, and you want to, for this set of pairs, you want to delete the minimum number of edges such that all pairs are disconnected. Somehow this is the dual of Steiner forest. All of this you can just solve on the trees. Almost all of them actually you can get exact solution, polynomial optimum solution in polynomial time. Even if not polynomial, it is not, you can get much better approximation. There are some cases that might be, you may need to get approximation on trees, but that is still much better and much easier than original graph. Then you just solve the problem and then solve the problem for the original tree. So that's the thing that we can do it. And this is like the beauty of this theorem. Now, okay, so I have mentioned this. I want to say a few words more about the proof of this. I mean, we cannot go, I mean, we don't go through the whole proof, but I want to just give some ideas about the proof. So, so because I have mentioned the actual problem and the actual embedding and the way that we can use it to prove essentially theorems, essentially solve the solution for cut problems. But let me just good. So let me just talk about something. Yeah, let's go here. So one thing that I wanted to one thing that I wanted to mention is that here in this probabilistic embedding into trees, I want to also connect this one with oblivious routing. I didn't connect it yet. So here we have T1, T2 to Tk. So these are the trees that we have essentially here. And each of them have, this is lambda 1, lambda 2 to lambda k. Now, how can we get oblivious routing? So the oblivious routing actually is, it comes directly from this one. So to get so when you get these trees, essentially with that, we had this property that the expected load is at most the expected load over the this equation essentially. We had this one, so this is at most B, and then B was ordered like it. So how can I get oblivious routing? Oblivious routing would be very simple. For any ST, I needed to route, I need to tell you how I route this path essentially for one unit of flow. Okay, so I will just do very natural things. What would be the natural things? Lambda 1, and we know that some of the lambda i's are equal to 1. So I will send lambda 1 of this essentially on the 3t. So I know that this S and T on this, say this is T1. So in this T1, I will find S and T. And on their path from here, I will, and this is the path because it's not spanning trees. Even if it's not a spanning tree, you can find the corresponding path in the graph. Find, essentially send lambda I unit of flow. So for any 3ti, I will just find the st, and I will send lambda I flow from S to T. So this is when we have this embedding into probabilistic embedding into trees. The original way that Rake had it for one tree, for the one tree is this oblivious routing. It was much more complicated because there you had only one trees, and essentially you need to use this kind of Steiner points in the tree to route this one. It is much more complicated. But here it is much easier because you just see this path and you just want naturally lambda one. And essentially, why do we have any oblivious routing? That very similar to the one that I proved essentially for mean bisection, essentially, or for bisection. You can say that if you do this one, because you have this property, then any flow that you will do it on these trees, like with any congestion. So this is essentially the thing that we have it. So suppose that we are given a convex combination of decomposition trees with maximum expected relative load beta. And suppose that we are given for each tree TI a multi-commodity flow that has congestion C in TI. Then the multi-commodity flow, this has a congestion at most BC on the when you map it to G. So you need to essentially prove two things. So first is that if you have some, so if you have if you route it here into trees, when you map it to the original graph, you essentially, if you have some congestion by the definition of congestion that I mentioned, the total flow that goes through an edge on these trees, and then you can multiply by D. So it doesn't change anything essentially, because if you multiply anything by demands DI, that does not change anything. So any flow that we have here, if you map it to graph G, then you will at most pay this additional factor B or beta essentially, which is at most log n, in the congestion. Why? This essentially comes from this fact essentially, because this, you know, that this expected load would be at most so the R load, so it's essentially the definition of this. So we know that the load here, comparing the load in the graph, comparing to the load in the original graph, would be at most trees comparing to graph would be at most log n more. So that log n more, which is beta essentially, just comes here. So if you have any routing here, if you do it optimally on the trees, essentially the congestion that you have at most beta times more. And and as I mentioned, because these are some paths on the tree, the so this you have again, I mean, to prove that this is like, if you consider any multi-commodity flow on these trees, if you map it essentially on the graph, you will pay at most beta more congestion. You are doing exactly the same thing. You will consider the optimum, and then you will map the optimum essentially here, and you can say that expected load here would be at most log n times there. So this is the same way that I have mentioned essentially for bisection. You can also prove that this exists for this one. So this is the way that you can get oblivious routing, and you get log n congestion more because you are doing through trees and not the original graph. So that's about this part. So this is the one that I wanted to cover. There is another thing that I want to give you a little bit about the proof of this. So this one I have essentially covered, I think, everything here. You can see, I mean, the exact formula here in the lecture notes. I think this is the address essentially. Go to network design, ascribe this, or in general, go to my homepage, network design course, and you can see the lecture notes there. And these are the exact formulation there, but this is the intuition. So let me clear this one and go next one to another things. So, and what about the proof? So, the proof of this. So, as I mentioned, so actually here. typical result that Rake had. Original stock 2008 result that Rake had. So he could obtain a convex combination of this decomposition trees with B or beta log n. So he was using the FRT result and a result by Charikar et al. This was Charikar, as I mentioned. So FRT can be de-randomized. So if you just use FRT the way that we described that, you can have exponential number of trees and then it is a probabilistic embedding. But you can actually get this T1 to T, and I think N was Tm, M is equal to N log N. So the number of trees here that you will get it. So Tm, say, where M is equal to N log N. So this is the result that Moses Chalkar had it, I think, alone or had some, I think, some co-authors as well, that it could show that this T1 to Tm, actually you can get them explicitly and these trees you can obtain it essentially. Rake used essentially the proof from FRT and these Chalkar results. And another result, this is called the minimum communication cost tree problem. So this is another problem. Ravi had papers on that one, and he's using these three results. So he used FRT, he used this de-randomization, and he used this kind of minimum communication cost tree. He combined all of them. He said that essentially you can get these results out of these three results, these three embeddings. That was the stock. However, there was a paper by Uri Feige and the second author that I don't remember. Uri Feige showed that actually this tree embedding and this Bartal, this Rake embedding, and this Bartal or FRT rank essentially embedding are just dual of each other. So that essentially he could prove everything using the min-max theorem. So what is the min-max theorem in general? So min-max theorem is a very simple thing. So I mean, the proof is not trivial, but essentially it says that if you have an LP and if you can write its dual, so if you write an LP, you can read more about it. I cannot go through the details of it because it can be another class essentially or several sessions there. So if you have an LP that you try to maximize something, you can write another LP which essentially minimize something. And there is a formal way essentially to get the dual LP from the original LP. You can even write a program to do that. You can just read it. So you can read it, and then from this LP, you can find another LP. And what is the important thing is that this you can show that this max and min are equal to each other. So essentially, the value of the LP and the value of dual LP, the optimal solution for LP and the solution for dual LP are equal to each other. This theorem, essentially, this is called duality theorem. Min-max theorem, essentially. Sometimes also it is called Farkas lemma. All of them are the same thing. Actually, the people obtain it in different contexts and different things, but it turns out all of them are the same thing, essentially. So Farkas lemma, min-max theorem, and duality theorem, all of them are the same, essentially. And what did Feige showed? Feige showed that this Bartal trees, or Bartal FRT, and the Rake are dual of each other. So essentially, essentially, you can get Rake using this min-max theorem, or Farkas lemma or duality theorem. So the Rake proof was just essentially using Barthal, but it was not just this kind of nice duality that Feige came and later showed and said that these are the same results. So, and I mean, going through, a little bit more details, you can read the paper of Feige on this. I think it was published somewhere. It was Feige, I think Anderson, if I remember correctly. But there was another quarter there. Mm. Good. Here. Okay, so what are the type of things that, for example, Feige showed? I just want to say that these are like some of, you can read actually from this as well. The proof are in the lecture notes as well, but you can see the original paper of Feige as well. That might be more revised essentially. But anyhow, this is the type of thing that the proof are, essentially, I just don't say the lemma, this is the thing. So that for any p greater than 1 and every family of the trees, there is a probabilistic mapping with distortion at mass p, if and only if for every non-negative coefficient alpha e, that the sum of the alpha e is equal to 1. Essentially, that means probably there is a treaty such that alpha e times dt of e over the g of e, this is distance one, is at mass p. As I mentioned, there is a corresponding between distance and capacity. So distance is equal to 1 over capacity. What's the meaning of that? So essentially, you can think about this. If this is two vertices here, and if the capacity is essentially a lot, means that these two vertices, so you can think about this one. You can consider it like a traffic network. If capacity of one edge is a lot, it means that the cars can go through this highway much faster. However, if the capacity is small, it means that it takes much longer for these cars essentially go through this network. So this is essentially the thing that says distance is 1 over capacity. This is a very good observation. Now, he essentially proves this one, that like essentially for every p greater than 1, if the family of trees, there is a probabilistic embedding if and only if we have this property. For every coefficient alpha e, such as some of them are equal to, there is a treaty such that essentially the expected distortion is at most rho. He shows, so this is the proof. You can read the proof here. There is a second lemma that he is also saying the same thing essentially. This is the way that he's making essentially the duality. He said that for every row greater than 1 and every family of trees, there is a probabilistic embedding of congestion at most row if and only for every non-negative coefficient beta e, there is a treaty such that the expected load is at most this essentially. Now, using this theorem, essentially, then we had these two lemmas in some sense. Then we had this final theorem. That says for every row greater than 1 and any family trees 1 and 2 are equivalent. What are 1 and 2? 1 and 2 are here. For every collection of lengths d, g, this is essentially the distances, there is a probabilistic mapping with distortion at most rho. And for every collection of capacities, CG, there is a probabilistic mapping with congestion at most rho. So essentially says that we have this kind of duality between these things. And here he's just using these two other lemmas that I have mentioned. So first he characterized what's the meaning of congestion, distortion at most alpha, And in this theorem is lemma 1 and this lemma 2, he essentially characterized what's the meaning of congestion be at most beta. Then he said that these two are equivalent. Why? Because okay, if we have one of them, then using this equivalence theorem, I can essentially, if I have the result for distortion, then I can change that one using this equivalence lemma that I prove to prove this theorem essentially for congestion as well. And vice versa. If I have this one for congestion, I can also do it for distortion for the distances as well. So this is essentially this theorem that we are talking about. And good. And one important thing. So this essentially is this kind of min-max theorem. I mean, this is essentially this is the way that you can just this Rose min-max theorem also is essentially the one that has been used here. So in the proof of each of these equivalence theorem, that is that, okay, we have a distortion P, then what's the equivalent there? There he's using essentially min-max theorem. So the question is that, so here essentially he's using this min-max theorem. So again, to prove it, first is that if you have a distortion, this distortion for distances, then I have an equivalent theorem. That equivalent theorem comes from min-max theorem. Then the same thing, also he proved that if you have congestion, I have this equivalent thing for the that using min-max theorem. And then this is the lemma 1 and 2. And then in the next one, and this theorem essentially is a very simple one. Given these two lemmas that are proved using min-max theorem, he just essentially plug in and say that if I have this one, then I can use this equivalence theorem in lemma 1 or lemma 2 to prove one way or the other. So this essentially, he says that these two are equivalent. And essentially, this says that everything that has been obtained by Rake in these two papers can be simplified. I mean, of course, it was not trivial at all. And this was very interesting result of, for example, Rake, that as just a simple somehow corollary of his result in STOIC 2008, he could actually get the best algorithm for much simpler algorithm for bisection. But Feige showed that essentially Bartal and or FRT and Rake are the same. And as I mentioned, always we had this concept that cut problems and connectivity problems are dual of each other. Like multi-way cut is a dual of a Steiner tree, or multi-commodity or multi-cut is a dual of a Steiner forest. But this is like a more formal way that essentially is done, and you can use it. Anyhow, so that's essentially the things that I wanted to cover about this multi-commodity flow, oblivious multi-commodity flow, as well as this kind of embedding into trees, either for cut problems or for connectivity problems. In the next few sessions, as I mentioned, we will talk more about some special graphs like planar graphs and some generalization of them, essentially generally sparse graphs, or a special case of a sparse graph, that for which we can get, here we talk, everything that we had was log n approximations. So far we talk about lots of log n approximations. So this log n was, say, for example, for set cover, for unique coverage, for these cut problems or connectivity problems. All of them had this log n essentially. I think the only exception was this K coverage that was 1 minus 1 over E was constant. Next, we talk about a special network, like, for example, for planar graphs. And again, generalization of H-minor free graphs, bounded genus graphs, and other sparse graphs, for which we get a p-task. And what is a p-task? P-task is 1 plus epsilon approximation for any epsilon greater than 0. So these problems, all of them are still NP hard on this special graph, so we cannot find the polynomial time algorithm. But we are talking about, especially bidimensionality theory, is a very general theorem that can obtain lots of algorithms, fixed parameter algorithms, as well as approximation algorithms on these graphs, and it can get 1 plus epsilon. And note that if the problem is NP hard, then p-task is the best thing that you can hope for. So we obtain the best result that we can hope for this graph. Interestingly, for lots of these problems, that we talk in general graph, this log n is indeed tight under some complexity assumption. For example, we mentioned about set cover, unit coverage, and several of other problems. We know that, or like for example, even this embedding, we know that this distortion that we will get in some sense for both cut and connectivity, log n is the best that we can hope for. We cannot go anything better than log n. However, for this special graph, actually we show that you can get p-task. 1 plus epsilon, it is the best that we can hope for. And that is interesting and important. Why? Because this says that if this is a general graph, you don't have any ideas about them, then maybe this is the best that you can do it. And by the way, we have also implemented this kind of tree embeddings, and they are working quite well actually in practice. So you can actually get these trees, solve the problem, and this is a very practical way if you want to solve any of these problems, because you just solve the problem, get the tree, solve the problem on trees, and then we solve the problem there. Here, there are similar things also that we are talking for this other special graph. And it is important, if you know that your instance has some structure, is more a special graph, it is not the worst case, then you should maybe use some other algorithms which are much better, and you can get 1 plus epsilon approximation. And there are lots of them which are also very nice and practical algorithms as well. So there we are talking about it. And interestingly, here the whole concept were based on the concept of trees. There it is again trees, a special graph, but these are essentially graphs of bonded tree widths that as I mentioned. These are like some kind of tree widths of a graph is the measure of similarity of a graph to a tree, and bonded tree width means constant tree width. These are somehow very similar to trees. There they are essentially playing the main role. Here, trees play the main role. Their extension, bonded tree width graph play the main role. And we will talk more about them, and then we talk about big graphs and what are the things that we can use, for example, streaming for them. And then we will go from there. Good, I stop here.